Hello and welcome to Wednesday Lecture. Once again, this is Sean Breslin. I'm coming at you for General Science 112. I just wanted to let you guys know about a couple of things. First of all, I'm going to do my best to kind of keep these little lecture videos somewhere around like 20-25 minutes, just hopefully that way it's a little bit more manageable for you all. Another thing that'll definitely help you now that we're starting to talk about actual science is that if you look underneath where you found this video, there's a little section called resource guides. This is just going to provide some handouts and kind of note-taking guides that you can use if you find helpful. You don't necessarily have to. I guess I imagine you guys printing them out and then kind of following along with the lecture and writing down uh, different things that kind of correspond to the lecture slides. I should also mention that for you guys in GS112 that at the end of just about all the videos that I make, I tried to do my best to include a couple of like reproductions of demos that I would normally do in class. That's kind of the part that I find the most interesting and most exciting, a lot better than listening to me talk at you. Um, so if you kind of watch the lecture video, just be aware that there's kind of another section that's kind of just, 1 or 2 minutes, something I've probably found from the web and stole, that has to do with different discrepant events, which are kind of just like really cool to watch and have all kinds of really great science in them, and also some really fun things that you can do with like family members and stuff like that. But just to kind of keep you interested, those will be at the end. Another thing which I kind of mentioned a little bit in another video, I believe, is that underneath where you found this video, there'll be a couple of different versions of lecture slides. One is what I call classroom lectures, and those are the slides that I'll actually be going through in the videos that I post for lecture. Underneath that, there's something called supplemental lecture slides, and that is kind of like I think of it as kind of like a textbook. Um, so like I said, I didn't have you guys buy any kind of like textbook, so I kind of supply everything myself. So keep an eye out for those. Without further ado, let's launch into our first lecture. So to start things off, the big question: what is science? There's a lot of misconceptions about science. A lot of people really do think of it just as kind of a body of facts that we just continually add to. But one of the things that makes science so special, it really isn't just a body of facts. It's really a process. And it is specifically a process for attempting to improve our knowledge of reality by actually making observations, right? That's really where science starts. You make some sort of observation. Could be an observation as simple as why is the sky blue, which turns out to not be a very simple answer, or just kind of an observation of something surprising. One of the things that I mentioned a little bit in the intro to this is I'll always kind of end the class with some sort of discrepant event that will hopefully kind of challenge some of the misconceptions. And if nothing else, if you guys have kids, there's some really cool demos that you can show them pretty simply. I wish I was in class to show them to you, but unfortunately that didn't work out. So that'll be kind of the best part. So our working definition in this class is of what exactly science is. Science is not just a body of facts. It is a process for improving our knowledge of reality by actually observing the world. And that's what empirical testing is. It's actually making observations. And I jokingly say you must probe the system in order for it truly to be science. And this results in some sort of rejection, confirmation, or modification of ideas. And even better than that, it's kind of a dynamic process that we're continually going back and forth, right? How many times have we heard something to the effect of, like, I remember when I was a kid, they'd say eggs were bad for you. And, then suddenly another study would come out and say, well, actually, no, they offer these benefits. And so it's this kind of back and forth that can frankly sometimes be a little bit uncomfortable because especially if you're like some of my friends in the math department, like they just want cut and dry answers. And science is very much a a dynamic process where it allows for change. So I kind of put together a diagram that is available in the resource guides that you should be able to find in a category on Canvas just underneath here. One of the things that drives me crazy is this idea that, oh, it's the scientific method. Well, yeah, it is technically the scientific method, but the problem is that the way that it's presented in a lot of textbooks for me is just kind of a linear process, right? It just kind of starts in one place and goes to the end, and all of humanity is, then improved. So the way that I kind of think about the scientific process is the following. The most important thing is an empirical observation, right? And all that empirical observation is, as I said, probing the system. You actually have to, make an observation of some sort, and you have to interact with the world in some way. Very next thing is, from some observation, you get some sort of new idea, and that's all that a hypothesis really is. Once you have a new idea, just like any of us would probably want to, test it pretty quickly, you would make sure that that thing was supported by a whole bunch of evidence, right? You'd probe the system in different ways. You'd end up with a whole list of examples of where your hypothesis kind of holds and where maybe it didn't hold out so well. And we'll talk specifically about what makes a good hypothesis as we kind of get through the class here. But one of the most important things is that that hypothesis is falsifiable. In other words, it has to be something that you can prove to be wrong. It's really a tough thing to prove it to be true, but proving it to be wrong is something that's a little bit easier. Once you've made that empirical observation and come up with a potential explanation for it that we call a hypothesis, and you've got supporting evidence, the next sometimes very painful part is sharing that with the rest of the scientific community. That's called peer review. That's going to be a whole week of us talking about exactly how that works. But when it comes right down to it, it's basically a bunch of haters just tear your work apart. And it really is a way to refine the idea, but it is really, really, really painful. I can tell you as having gone through it several times. And another really special thing about science is that this peer review process, actually, you are able to peer review other people's work, right? And so even though, I submitted a bunch of work for publication, and they tear it apart, I occasionally got to kind of, helpfully give some helpful criticism of other individuals. But this is really where you either, you make or break it, right? If the evidence doesn't really support your hypothesis, the scientific community really is going to kind of reject that idea. But, every once in a while, the evidence supports the hypothesis. People have actually been able to repeat your work, and you get to the point where, they get some sort of tentative acceptance. One of the things you'll notice here, this is always very tentative, right? You're always kind of expecting something to go wrong. You always kind of expect, especially with a brand new idea, that it maybe is not as true as you might at first believe. Once that tentative acceptance of your hypothesis with its supporting evidence has been made, one of the most important things in terms of this method that we're talking about here is that those other researchers will actually go in and repeat your work, or they'll repeat your work with some other hypotheses of their own. And what quite often happens is that more research kind of either refines or rejects your original hypothesis, and then the whole entire thing kind of starts all over again. So this is a really nice view of the way that science is actually supposed to work. I did locate this pretty nice, computer animation of another good way of thinking about this way of doing science or understanding the way that science is done, so that we're going to just transition to that in just a second. One of the resource links in your syllabus includes one of probably one of my favorite kind of animations that also gives you a little bit more detail in terms of how the scientific method actually works. And that's this one. And so if you go there, you'll actually be able to kind of go over a couple of these bubbles here. Here's just kind of a different look of one particular section of how I was talking about the scientific method working. But here we see the hypothesis and the kind of your predicted observations and the actual observations and kind of the different paths that some of that the evidence can point you towards. You can maybe go to an opposite hypothesis, or you can maybe develop a new hypothesis. So another part I like about this is that it also includes right at the top this idea of exploration and discovery. And it really is about being observant and just being having kind of natural curiosity about the world. And one of the things I love about this too is that it also talks about serendipity, and that plays a huge role in the text that we'll be reading, the T-Rex and the Crater of Doom. Here's an excellent example of how important the scientific community is, and a little bit about the publication process and the way that theories are actually built up. And then probably the whole reason you do science, more than just being naturally curious about the world, but it leads to some very real benefits and outcomes. I know I'm a type 1 diabetic, and the insulin that I use on a daily basis comes from a genetically modified E. coli bacteria. So, there's an example of application of science that is literally keeping me alive. One issue that I thought was an important one to kind of get straight are the definitions of three terms, one being theory, the other laws, and the other scientific fact. So I just wanted to talk just a little bit about definitions of those pretty specific and very different terms. One is a scientific law, right? We hear about Newton's law, for instance, that objects in motion will tend to stay in motion unless acted upon by an outside force. In chemistry, there's something called the ideal gas theory that allows you to predict a pressure if you're given a certain volume amount of gas and temperature. All of these things are actually descriptions of nature. A law is specifically a description of how nature behaves in a predictable way. It is definitely not an explanation of why it does so. So in that first example, Newton's first law, it doesn't say anything about why that particular thing happens, why objects continue to stay in motion unless acted upon by an outside force. It just says that's what it does, right? And so laws are actually just descriptions and not explanations. Honestly, it's much easier to come up with a law. The other side of this coin is another term called a theory. And theories are actually those things that suggest explanations. And it's not just a simple explanation, right? Any one of us could come up with a simple explanation for something. But it has to be supported by a significant body of evidence, and that entire scientific community has to, at least the majority of them, has to agree. So that's what a theory is. And one of the things that is very difficult with our kind of our everyday life, if somebody says, oh, that's just a theory in everyday life, it's a very different meaning. Like the way that we use theory generally is a very kind of low bar, whereas in science, if you call something a scientific theory, it has to be in a pretty ironclad explanation. And that leads to another commonly misconstrued idea in the public, and that is what a scientific fact is, right? When you say a scientific fact, it has to mean that whatever observation or theory or law that you're talking about is something that's kind of agreed upon by the scientific community, right? And they have to be the experts in that particular area that agree that that evidence is strongly supportive of whatever concept, whatever observation, idea, or theory that you're talking about, right? And so a scientific fact, which is a little bit given this definition of the way that we're talking about facts, right? They're actually a fact now, right? They're always open to change or modification, but whatever that change or modification is has to have a whole bunch of evidence to actually kind of either refine or refute the fact. So now we come to a section which I call the characteristics of science. I have 7 of them. At least that's the way I've kind of organized things. We've already talked about a few of them, but we're just going to kind of run through a couple of these. So the first one that is something we've already talked about real quickly is the idea of falsifiability. So this is essentially saying that scientific claims must be testable to be considered within the realm of science. I like to think about this testability as something kind of written as an if-then statement. A good example of this might be, let's say that we're looking at, we happen to make an observation that, our garden plants tend to kind of seem to grow towards our grow lights or something like that in our greenhouse. Of course, we're growing only things that are legal. So first thing that you might notice is that, well, if I move the light, it seems to follow it a little bit. And so you might actually make some sort of hypothesis in an if-then statement that says, if I turn off the light in my greenhouse, then my plants will die. There's a good example of a falsifiable way of doing things, right? And you can turn the light on in your greenhouse, and if the plants grow, then you'd say, oh, that seems to support it. And then if you turn the light off, then the plants die. But if it has nothing to do with the light in your greenhouse, right, and you say you turn off the light and the plant seems to live regardless of what you're doing with the grow light, it's probably due to something else. Another important thing about falsifiability is that there must be the possibility that some observation, experiment, or other evidence could make a reasonable person conclude that a claim is false. One of my favorite quotes is from Carl Sagan, who would always have this program where he'd say, "There's billions and billions of stars." But anyway, he was an astronomer. He said famously that there are many hypotheses in science which are wrong. That's perfectly all right. They're the aperture to finding out what's right. Science is a self-correcting process. To be accepted, new ideas must survive the most rigorous standards of evidence and scrutiny. Notice that it's okay to have a hypothesis which is wrong. That's actually built into the system to have hypotheses that are wrong. Another thing which often gets me into trouble is this idea of that science has to focus on naturalistic mechanisms. The explanations in true science have to involve some sort of natural testable process. Many people kind of think of this as precluding the existence of a God. In my opinion, they kind of deal with 2 different things. But the important thing is that the exclusion of like supernatural influences or the supreme being or God, it's really a pragmatic reason. The second that you say that something that is above us is in charge of everything else, then anything becomes possible, and so it is therefore not falsifiable. And so this idea of not being falsifiable absolutely precludes this thing from being considered science. And quite honestly, there's multiple times in my own field of organic chemistry that they would invoke something supernatural to describe, but usually it had something to do with the fact that we just didn't have a complete understanding, and usually it's a relatively temporary thing. My third principle of science is replication, and this is the requirement that a researcher has to have their work duplicated by other completely independent researchers, right? And this work done to replicate results is generally something that has to be done by people that don't really have any skin in the game, right? It's not, they don't have any kind of vested interest. Just have to make sure that by replicating things that uh, perhaps you're going to be able to eliminate some human error. And actually, in I think about 2 weeks, we're going to talk about both faulty perceptions that human beings typically have, and also the kind of the role of bias. We all have biases, and scientists do too, and it's just really difficult to kind of ferret those out. This need for replication is something that the kind of open communication in the scientific community is the germane part of. And also a part of this, and one thing that I often struggled with in my like experimental sections and such, is that you have to be very specific about the methods and materials that you employ. One of the most painful sections to write is an experimental section for that reason, because you have to literally give somebody like the cookbook for setting up whatever experiment that you've had. And quite often, like if you're not clear, then somebody tries to replicate your work and they think either you're an idiot or that it's that, you know, worst case scenario, you're lying about something. But that's something that the scientific community is very careful about. And the final one of the 7 that we're going to talk about today, we're only going to get into 4 because I noticed the video's kind of dragging on towards like 25 minutes or so. I'm trying to do my best to keep these down to 20 so that people will actually watch them. Is this idea of empirical evidence, right? And this is just the idea that in true science, there has to be objective data carefully collected through observations and actual experiments in an attempt to reduce error and bias. Honestly, the best kinds of evidence are those that lead to the ability to predict brand new situations. And the one thing that is really tough, especially with the public, is that in science, if the predictions are correct, then the idea is strengthened, but it is never proven, right? Those words you should never hear a scientist utter, and it happens all the time. So the next time that you hear, somebody on the news talking about something that scientists have proved, scientists are not in the business of proving. We are in the process of strengthening theories. Okay, I think we're going to leave things here. I hope that you were able to view the presentation up to this point. Assuming everything's working well, I'll see you on Friday, and we'll talk about the 3 remaining principles of science. And we'll also, in a little bit more fun, we're going to talk about just real briefly what happened in the discrepant event that I'm going to append to the very end here. So stay tuned for the discrepant event of the day. It's one that I would usually do out in the UCC parking lot and scare everyone and nearly run people over. So it's probably safer this way, but it's not nearly as much fun. So stay tuned for that. And then I will talk to you again on, actually, technically we have labs. So I'll talk to you on Thursday.
We are on location today for a never before attempted Imagine It. I have Carl Nelson with me. We have our safety belts on. What are we doing today?
We're going to talk about Newton's laws of motion in our outreach van.
Okay.
So right now, this van and everything in it is at rest. And we're going to stay at rest unless we somehow accelerate down the road.
Right.
So that's what we're going to do.
Okay.
We've got a passenger here who's kind of unbelted. He does have a string, but we're going to see what happens when we accelerate down the road.
All right, so we are watching our yellow passenger.
Yeah, and ourselves. So.
Sure.
So we got Sarah in the driver's seat. Sarah, go ahead and just punch it. Floor us.
So we moved.
We moved. Okay. All right. Gentle stop, Sarah. And did you notice the balloon initially moved backwards?
It did.
Just like our bodies did, because we were actually at rest, but the van started to move, and the seats actually collided with our bodies.
Huh.
Right?
Pushing us a little forward in the back?
Well, yeah, kind of. It feels like we get pushed into the seats.
Yeah.
But it's really our bodies at rest, and the van runs into us.
Huh.
Okay.
So we were never moving.
Well, we did.
You're saying.
Once the van caught up to us, then it started pushing us forward.
Okay.
Okay. Same thing with the balloon. It was initially at rest, and it started to move backwards. Sarah, just give us a little burst. See how the balloon comes back?
Yep.
Okay, gentle stop. So we're going to see what happens, though, if we put a balloon filled with helium gas in front of us.
Okay.
Okay, because
and this one's just blown up with...
this is regular air.
Okay.
But everybody's probably experienced this in a car, right? You're in a car, someone floors it. Move your foot for a second. A balloon right there. So we have a balloon that's floating, a balloon that's just hanging in the air, and we're going to see if there's any difference. And Blake, what do you think? Would there be a difference? Just because it's floating?
I don't know. I think that maybe this one will be a little bit more grounded. Because I don't know. That's just that's my hypothesis.
Let's try it. So Sarah, go ahead and punch it. All right, emergency stop. Stop. Yeah.